All right, let's craft the code on something you probably do a dozen times a day without even thinking about it. Your Android unlock pattern.
I mean, have you ever stopped to wonder just how many different ways there are to unlock your phone with that little grid? You just swipe and boom, you're in. But the real number of combinations, it's way, way bigger than you'd think. And how we figure that out? Well, that's where things get really interesting.
So we're going to dive right into the logic behind that standard 3x3 Android grid. For us, today, it's not just a security thing, it's a full-blown mathematical puzzle. Our mission is to count every single valid pattern. And to pull that off, we kind of have to learn to think like a computer. So here's the game plan. First, we'll get the rules of the puzzle straight. Then, we'll figure out how to explore every possible path. We'll tackle what I call the jump rule. It's the tricky one. After that, I'll show you a really cool shortcut using symmetry, and then, finally, we'll put it all together and count up all the valid patterns.
Okay, so what exactly are we trying to solve here? Well, this Android pattern puzzle is a lot more than just connecting some dots.
There are some key rules of the grid. Rule 1, every dot in your pattern has to be unique. No reusing dots. Rule 2, and this is the important one, you can't just draw a line that jumps over a dot you haven't used yet. And finally, Rule 3, the pattern has to be a certain length. For most phones, that's somewhere between 4 and 9 dots long.
Now let's zero in on that jump rule, because it is absolutely crucial. So check this out. Connecting dot 1 straight to dot 3? That's invalid. If you haven't visited dot 2 yet, you're illegally jumping over it. But let's say your pattern went from, 5 to 2, and then you want to go from 1 to 3. Well, since dot 2 is already part of your path, that move is totally valid. See the difference? It's all about the order.
Okay, so we've got the rules. Now, how in the world do we find every single valid pattern? The best way to picture this is to think of the grid as a maze. Our job is to navigate that maze and find every possible path.
Right, so how do we do that? How can we systematically find every path without getting lost or, even worse, double counting things? We need a solid strategy, a system that lets us explore everything methodically.
And that brings us to our chosen strategy, depth first search, or as we'll call it, DFS. If you've ever dabbled in computer science, you'll know this one. It's a classic, and it's absolutely perfect for this kind of maze-exploring problem.
So what exactly is depth first search? Well, stick with that maze analogy. Imagine you're standing at the entrance. Instead of peeking down every single hallway right away, you just pick one and go. You follow that path as far as it'll take you, as deep as you can go. Once you hit a dead end, you backtrack to your last choice point and then try a different path. You just keep doing that. That's really all DFS is.
So, let's apply that to our grid. Here's our approach. First, we pick a starting dot, say dot 1. Then we explore one path as deep as it can go. Maybe we go from 1 to 2, then from 2 to 5, and so on. As we're building these paths, we're constantly counting the ones that are of valid length. And whenever we hit a dead end, nowhere else to go, we just backtrack and try a different branch. Simple as that.
Okay, so the strategy makes sense, but how do we actually handle that tricky jump rule? How do we translate that logic into code so the algorithm knows what to do?
This is where things get really clever. We just create a jump rule book ahead of time. It's basically a table that tells the program, hey, if you're thinking of going from dot 1 to dot 3, just so you know, you're jumping over dot 2. Or going from 1 to 7, you're jumping over 4. It has every possible jump pre-programmed. It's genius. And all of that logic, that entire rulebook, gets boiled down to this one little bit of code. This is it. This is the engine. Now, I know it looks a little technical, but trust me, the idea behind it is super straightforward. Let's break it down. So that code is basically asking two simple questions every time it considers a move. First, is the next dot unvisited? And second, is this path either a direct connection or, if it's a jump, is the dot I'm jumping over already visited? If the answer to that whole check is yes, then boom, the move is valid. So at this point, we have a working algorithm. We could just run it from all 9 starting dots and call it a day, but that's not very efficient, is it? This is where we get to the really elegant part of the solution, the big aha moment, and it all has to do with symmetry. Seriously, think about it for a second. Do we really need to run our search from all 9 different starting points? I mean, look at the grid. Is there really a difference between starting in one corner versus another? No way! The grid is totally symmetrical. The number of patterns you can make starting from a corner dot like 1, is going to be exactly the same as starting from any other corner, like 3, 7, or 9. You can just rotate the grid and the paths are identical.
And hey, the same thing goes for the edges. All those patterns starting from an edge dot, like 2, 4, 6, or 8, they're all symmetrical too. They're basically the same starting point, just rotated. So what does this mean for us? It means we don't have to do 9 full calculations. Nope, we only need to calculate for 3 unique starting types: a corner, an edge, and the center. That's it. This little shortcut is a huge time saver.
All right, time to count all the valid patterns. Let's bring this all together.
So the final math is actually pretty elegant. We find all the patterns that start from dot 1, a corner, and we multiply that by 4. Then we find all the patterns that start from dot 2, an edge, and multiply that by 4. And finally, we find the patterns from the center, dot 5. Well, there's only one of those. We add them all up, and that gives us our grand total.
So what's the answer? Well, just for fun, if we were looking for patterns that are only 1 or 2 dots long, the algorithm tells us there are exactly 65 of them. And of course, we can use this exact same logic to find the total for the real security patterns, the ones between 4 and 9 dots long.
It's just such a perfect example of how a problem that seems really complex on the surface can be broken down and solved with a clear strategy and, a little clever insight. It really makes you wonder, right? What other everyday tech that we use, our GPS, our social media, what elegant algorithms are hiding just underneath,